Welcome, ladies and gentlemen. So I want you to think back to some integration techniques that we developed first semester when we introduced U-Substitution as a technique for integrating integrand functions that consisted of two parts, right? Where one part was a derivative of the other or a portion thereof. Up until this point, and on our unit assessments, we said you don't have to use U-Substitution as a technique for integrating, right? So long as you know your derivative rules very well, right? And can recognize the relationship between the two pieces using your knowledge of the chain rule, right? Which part is the derivative of the other part, and so on and so forth. Well, there are two instances where we have to use U-Substitution in accordance with the AB curriculum. One of those is kind of an algebraic rewrite, which will enable us to rewrite an integrand function, right, in such a manner that we can integrate using the techniques we have where previously we couldn't. And the other is called change of limits, where we're going to do a U-Substitution and change the limits on our integral symbol and go ahead and evaluate that way. So we're going to take a look at those at the first part of today's class period. The second content objective for today will be finding derivatives of inverse functions, okay? Finding derivatives of inverse functions. And this is shown up on the multiple choice section. You typically have 1 or 2 questions, and not so much on the free response, but it has shown up on the free response. The concept has in years past. And so we're going to take a look at that. And then lastly, you'll have a chance to work on your concept and skill guide. So let's go ahead and get started. Everybody find your day 5 note sheet, please. I want you to be ready to share how we integrate, right, each of these expressions. And so if we were to evaluate that first indefinite integral, could we integrate that? Right? Could we find an antiderivative function for that first integrand function? Kyle?
Yeah, like raise it to the next power, so we get to square root of x plus 1 squared, and then take the antiderivative of that inner function. So you do the opposite of the chain rule.
Yeah. For this particular expression, we could use the power rule and go term by term, right? We could do the power rule and go term by term. And so yes, we'll be adding 1 to the current exponent, which is 1/2, dividing by the new exponent, and then integrating, right, the second term, because it's just a sum or difference. And so absolutely, we can handle this integration by going term by term. So let's do it. We'll go ahead and start off with my current power function x to the 1/2, and we'll integrate by adding 1 to the exponent and dividing by the new exponent. So that would become x to the 3/2, and then divide by the new exponent. Dividing by 3/2 is the same as multiplying by 2/3. So for that first term, I get an antiderivative function that's 2/3 x to the 3/2. Yes? Term by term, continuing on, plus an antiderivative for 1 with respect to x is x. And then always, if we're evaluating an indefinite integral, want to make sure we include a constant integration, so we do our plus c. Everybody good? Can we integrate the second? Can we integrate the second integrand function? So can we evaluate that? Hayden?
Yeah.
Term by term again, so we've got a sum or difference in my integrand function. We'll go term by term, and so it looks to me like we already know the antiderivative of the square root of x. This would be 2/3 x to the 3/2 plus an antiderivative for x would be power rule again, 1/2 x squared, and then plus c. Actually, we're gonna do some boxes here, eh? Ooh, very nice. Thank you. Like that box. Nice. Take a look at the third indefinite integral. Are we able to evaluate that, right? Are we able to evaluate that? What do you guys think? You think we can do that? Riley?
If you distribute the root x to each term in the parentheses, you can do it.
So as it's written right now, that square root of x is not the derivative of quantity x plus 1, or vice versa. X plus 1 is not the derivative of the other piece, right? Square root of x, as if you consider these two algebraic pieces separately. And so this is not undoing a chain rule, but we can utilize algebra to rewrite the integrand function, right? And then go ahead and integrate term by term. Absolutely. Perfect. Thank you, Riley. So let's go ahead and rewrite, right? Not integrate, but rewrite. X to the 1/2 times x to the 1 is currently x to the 3/2 plus the square root of x times 1 is still just x to the 1/2, and so we've distributed and rewritten using algebra in such a form that now we can go term by term, like Kyle was saying. Originally, we can only go term by term and integrate. So now we would go ahead and do x to the 3 halves plus 1 would be x to the 5 halves, divided by the new exponent would be 2/5 x to the 5 halves, plus term by term 2/3 x to the 3 halves, plus c. Okay, one to go, and in our last indefinite integral, we've got two distinct algebraic pieces again. We've got the x to the first out front, and then we've got the square root of quantity x plus 1. Are we able to evaluate that final indefinite integral? Right? Are we able to evaluate that final indefinite integral? What do you think, Riley?
No.
Yeah, currently, right, we don't have the techniques or tools to evaluate that last one. How come? What is it that's making that last one unable to evaluate where we could evaluate like that third one, even where the one piece wasn't the derivative of the other, right? What's keeping us from integrating that? What's holding us back? James?
You can't distribute the x out in front, and like one is not the derivative of the other.
Absolutely. If one algebraic piece were the derivative of the other, right? If x were the derivative of x, we could go for a power rule where the overall power, right, was base x plus 1 and then to the exponent 1/2, but x isn't the derivative of the x. Nor can we distribute algebraically as we did in the third one because we've got quantity to the 1/2, right? And my exponents are a higher order of operation, right, level than multiplication, so we can't distribute through there. Absolutely, James, thank you. So what are we going to do? Well, we're not going to quit. We're not going to throw in the towel. As a matter of fact, we can evaluate that using U-Substitution. Okay, and so we're going to use U-Substitution, and this is one of the cases where we have to be able to use U-Substitution, whereas we didn't have to use U-Substitution in our previous unit assessments. So let's go ahead and evaluate that. So we'll go ahead and take a look at our original x times square root of x plus 1. Whether there were limits or not, U-Substitution is going to be our ticket to evaluation. What we're going to do is combine that with our change of limits just so we can rewrite that expression with a new variable. Instead of having x's in my integrand function, we'll have u's in my integrand expression. So here we go. I'm going to let u equal. Well, I need to choose u so that I can rewrite this in such a way where I can utilize algebraic techniques to evaluate this. And so the problem here was that my quantity was inside of the radical, and I couldn't distribute the outside factor. Versus last number 3, the third one, my quantity was x plus 1, and then inside the radical wasn't a quantity, it was a single term. So let's go ahead and choose u to be quantity x plus 1, and I'd be working towards having a root u there, which is a single term inside of a radical expression. If u equals x plus 1, right, then that x out front, that x out front could be rewritten in terms of u. How would I solve this? How would I solve this for x? Well, I'd subtract over that 1. So x would equal u minus 1. And so as I'm working towards this u substitution, I can see this x out front would be given by u minus 1. And I can see that this square root of x plus 1 is going to be the square root of u. So you guys see how by choosing u to be that quantity, x plus 1, we can rewrite it and so that the term inside the radical is no longer a quantity, it's just a single term. Why is this helpful? Well, it's helpful because now this resembles our third integrand function. I can distribute the root u through that quantity, u minus 1, and go algebraically term by term. However, we're not done. We haven't written my integral symbol with the new limits. What do you mean new limits? Well, if I'm integrating with respect to x in this first integral, what kind of values are these numbers? They're x values. I've now rewritten my integrand function with u's in it. And so when I integrate this with respect to u, I need to have u values here. The limits are no longer 2 to 5. So let's go ahead and go over here and see if we can't complete this u substitution. If u equals x plus 1, then du dx would equal 1, and du would equal dx. So it looks to me like we can do a straight substitution. Dx is going to be du, which is great news because I need a du, right? I need to know with respect to what variable anytime I have an integral symbol. That's telling me my independent variable and my antiderivative function will be used. Last thing is I need my limits. And so if u equals x plus 1 and my current x values were 2 to 5, what would u equal when x equals 2, my lower limit? U would be 2 plus 1 is 3, right? Wouldn't it be 3? So I can just use my variable definition for u, which is my x value plus 1. And my current x value was 2, so when I do the substitution, 2 plus 1 is 3. It looks like we're going to integrate from 3 to when x is 5, then what is u? 6. All right. So we've gone ahead and completed our U-substitution. We've utilized change of limits in order to rewrite the limits on my integral symbol, and now we can integrate using algebra. So one more rewrite. We've got to keep my integral symbol until I rewrite this in the form I recognize. I'll use the distributive property to multiply the square root of u through the quantity u minus 1. That would be u to the 3 halves minus u to the 1 half. And we're going to integrate that with respect to u. And then we'll evaluate using my new limits. And so here we go. Term by term. U to the 3 halves will integrate to 2/5 u to the 5 halves minus u to the 1 half will integrate to 2/3 u to the 3 halves, and we'll evaluate that from lower limit to upper limit. So it appears as though we get 2/5 u, we get 6 to the 2/5 times 6 to the 5 halves minus 2/3 6 to the 3 halves minus, oh goodness, 2/5 times 3 to the 5 halves minus 2/3 times 3 to the 3 halves. Right. So we could do some rewriting if we wanted to, but the point of this wasn't to evaluate and get a final answer. The point of this was to rewrite in a form that we could integrate using techniques we've already developed and to practice changing our limits. However, I do want to verify that using the original with limits 2 to 5 and x's numerically would produce the same result as algebraically evaluating after the U-substitution. So let's go ahead and go to our graphing calculators and math 9 each of these. So I'm going to go ahead and math 9 each of these. And we'll compare. All right, so we're going to enter 3 things. What? Well, our first thing, we want to numerically do the one we couldn't evaluate algebraically. So numerically, let's go ahead and math 9. Math 9, from 2 to 5. The expression x times square root of x plus 1. Close radical, close expression, dx. So that's telling us about 22.703. Now let's go ahead and numerically evaluate our rewritten u expression giving change of limits. So we'll do math 9. And we're going to do 3 to 6. Our rewritten expression was quantity u minus 1, so that'll be quantity x minus 1, times square root of u, so that'll be square root of x. And let's compare these values. Woohoo! 22.703. So we've successfully done a change of limits. And lastly, if we were super slick, we could see how our evaluation went. boy. How long is this going to take? Uh-oh. Longer now. Huh. I think of it as an exercise. You guys watching? Are you guys catching me? Good. When I make a mistake. Why even pause? Right? What's done is done. If I made a mistake somewhere there, it's going to show me right here, but I went for it. And the fruits of our labor, by golly, we've generated 3 different expressions. Each of them are equivalent to the same thing numerically, 22.703, and that's where the screenshot, Kyle. That isn't PDFable. I don't know what is. I don't know where I'm going to fit it, though. Just have to get it where you fit in. Awesome. What questions do you guys have about our change of limits? So we use U-Substitution to rewrite the integrand expression in such a way where we could use algebra to rewrite in a form that we recognize and integrate term by term. Let's go ahead and practice one. So let's go ahead and consider my original expression. We could do this problem either way. Right? We could do this problem either way using our knowledge of the chain rule, but I want to use it as a platform for practicing our new method called change of limits and U-Substitution. So let's go ahead and choose U. Let's choose U to be that e to the x. We let U be e to the x. I'm working towards rewriting my integrand function as U over 1 plus, and then e to the 2x is the same as e to the x squared, right? And e to the x squared is U squared. And so I'm working towards rewriting this integrand expression as U over 1 plus U squared. By rewriting in this way, we're thinking this is an overall what kind of rule? What kind of rule is this looking like? Ooh. I'm not liking this. I don't like this at all. We're going to have too much. We're going to have too much. If I do U as e to the x, let's see what our dx is, and I think that this e to the x is going to be taken care of. So let's let U be e to the x, but let's do the derivative of both sides. Du dx then will be given by e to the x also, and there we go. Now we can see how this is going to work out. This means that my dx times e to the x is going to be what du is equivalent to. So it looks like this dx e to the x. There we go. This e to the x dx is equal to what? Is equal to du. And so when I go to substitute for this entire thing, I don't need an extra u. Then I have too much. I'd have too much u. E to the x dx is equivalent to du. Everything in my integrand function is accounted for now, except for my integral symbol and change of limits. So let's go ahead and rewrite our integral symbol and consider our change of limits. Right? What are our change of limits going to be? What are our new limits going to be? Well, if we've let u be e to the x, then when x, my x values from the original, when x is 0, what is u? When x is 0, u is e to the 0, which is 1. Good job. So 1 is my lower limit in terms of u as a u value. When x is ln of 5, right? When x is ln of 5, what is u? What? When x is ln 5, u is e to the ln 5, which is 5. Awesome. All right, let's complete it algebraically and then do our same check with the graphing calculator. But first, non-calculator algebraic. What relationship now am I going to be using? What overall antiderivative rule will we be using when we integrate this? Right, what antiderivative rule is this? Yeah, inverse tangent, right? This is inverse tangent. The derivative inverse tangent is 1 over 1 plus the argument squared times the derivative of the argument. And so this is going to be inverse tangent of just u straight up, right? So this will be inverse tangent of u straight up. There's my antiderivative. And we'll evaluate that from 1 to 5, which means I get inverse tangent of 5 minus inverse tangent of 1. And while this first one doesn't reduce nicely, we certainly know the inverse tangent of 1, right? The inverse tangent of 1 is the angle whose value of tangent is 1. What's that? What's that? Almost. Power 4, right? Power 4. 45-degree angle, so power 4 radians. Awesome. All right, let's go ahead and try it out. We're going to do a triple check. A triple threat. What? No, not a triple threat. A triple check. So here we go. We want the math 9 from 0 to ln 5 of, oh boy, how am I going to write this? I'm going to go e to the x over quantity 1 plus e to the 2x close quantity with respect to x. Maybe. All right, now we're going to go ahead and do our rewritten change of limits U-Substitution, right? In that definite integral and see what we get there. So math 9, and I get 1 to 5. And my integrand function is 1 over quantity 1 plus x squared. Hey, and we'll check our algebraic eval where we got inverse tangent of, I better check my mode before we do any of that business. Where we get inverse tangent of 5 minus pi over 4. Huh? Survey says, oh my gosh, killing it. We are definitely exporting this bad boy. I love it. I love it. Cool. All right, so I want you to know that this change of limits business right here from the 0 to ln 5 and the 1 to the 5 is more likely to show up on a multiple choice question where you don't go all the way to the end and evaluate. It'll be something like, this indefinite integral is equivalent to which of the following? And it'll give us A, B, C, and D. And one of the and E. And one of the choices is going to be 1 over 1 plus u squared du from 0 to ln 5, where they don't change the limits. You know what I'm saying? They're going to give you the correct U-substitution portion for the integrand, and then leave these limits, right, that 0 to ln 5, and that's why we have to be comfortable with the change of limits. If this were on free response portion, then you might be expected to go all the way to the end, in which case you could resubstitute after doing your antiderivative. You could resubstitute in the u as e to the x if you wanted to, and that would still be fine. You know what I'm saying? But the change of limits would be needed here to match up a multiple choice question for sure. What question do you guys have about the change of limits? Then we're one hodgepodge content objective away, and then we just have a single unit left involving particle motion. We've got position, velocity, acceleration. So let's go ahead and take a look at our inverse function. Let's suppose now, back a blast from the past from algebra, advanced algebra, if f and g are inverses, right? If f and g are inverses, then the composition of f of g of x or g of f of x, right, is equivalent to what? Well, whatever one function does to this original input, right, x, then this inverse function is going to undo that and get you right back to where you started. In other words, f of g of x is going to be equivalent to x, my original input, and g of f of x, right, since g and f are inverses, would be equivalent to the original input x. And so two inverse functions undo one another. Whatever my first inner function g does to my input x, the inverse function f will undo it and vice versa. Well, that means for us that f of g of x equals x, so if we differentiate each side now to get our derivatives involved, think about what rule we use on the left-hand side. Sorry, that's going to bug me. So if we differentiate both sides with respect to x, what overall rule would we use on that left-hand side? What overall rule would we use to differentiate f of g of x, the composition of functions? Kobe?
Chain rule?
The chain rule, comma baby, good. Where the derivative of a composition of functions is the derivative of the overall function with the inner function. In this case, the inner function is g of x times the derivative of the inner function. What, pray tell me, is the derivative of my inner function? Well, the derivative of my inner function is g prime of x. That's going to be equal to then the derivative of the right-hand side. The derivative of x with respect to x is, I got this one, guys. 1. Seinfeld, I'm out of here. Put one on my head. Derivative of x with respect to x is 1. All right, so what do we care about? Well, we care about the derivative of this inverse function. That's our final thing. We want to consider what the derivative of g is, right? Given information about f and g, the derivative of g, right, is g prime of x, and g is the derivative of f, so that's what we care about. Let's solve for this and see if we can apply it to the problem. So I'm going to solve for this red g prime of x. This means that g prime of x, if I were to solve for it, would be given by 1 over that f prime of g of x. And this is the result then that we'll be using, right, in order to find the derivative of an inverse function. So we just use the definition of inverse functions. Their composition is equivalent to x. We differentiate both sides to get the calculus involved, the derivatives involved, and now we'll use this result, g prime equals 1 over f prime of g of x, in order to evaluate the derivative of an inverse function. Let's try it in the context of a concrete function. So let's suppose that f is given by x cubed plus x. And let's suppose that h is the inverse of f. And so I took this directly off of a multiple choice question from a previously released exam. Let's find h prime of 10. All right? So f is given by x cubed plus x, h is the inverse of f, and we're asked to find h prime of 10. What's the relationship between f and h? Well, f and h are inverses of one another, right? F and h are inverses of one another. That means that, right? That means that f of h of x is equal to what? Is equal to x. This means that if I were to differentiate both sides, as we just did, the left chain rule differentiation would produce f prime of h of x times the derivative of the inner function would be h prime of x equals the derivative of the right-hand side. The derivative of x with respect to x is 1. So h prime of x, right, which I'm asked to evaluate at x equals 10. I'm asked to find h prime of 10. H prime of x is given by what? Well, it's given by 1 divided by f prime of h of x. Tricky, Ricky. Okay, so what is our task? our task will be able to evaluate, right, this h prime expression. So we need a couple things. Firstly, we know that h and f are inverses, right, are inverses, which means that the ordered pair, right, x comma y on f corresponds exactly to the ordered pair y comma x on h's, right, on h's graph. And so let's see if we can't use that to our advantage. I'm trying to evaluate h prime of 10, right, h prime of 10. And so h prime of 10 would be a y-coordinate on f. And f's a y-coordinate. If I could figure out an x-coordinate that corresponds to that y-coordinate 10, right, then I know what h of 10 is. 2 through inspection. So the point 2 comma 10 is on f. This means that, right, this means that if 2 comma 10 is on f, what must be on h? What's that? 10 comma 2. All right, how will that help us? Well, let's see. We want to find h prime of 10. H prime of 10 will be given by 1 over f prime of h of 10. And h of 10 is equal to what? 2. And so we can replace this h of 10 as 2 and rewrite and finally evaluate. So h prime of 10 is given by 1 over f prime of 2. Gosh, we're so close I can almost taste it. Can we evaluate f prime of 2? Well, we weren't given f prime, we were given f, but by golly, we've got some differentiation tools, don't we? And so if f is x cubed plus x, what is an expression for f prime? Kyle?
3x squared plus 1.
So f prime of x is 3x squared plus 1, thank you, which means that f prime of 2 is 2 squared plus 1, which equals 13, is that right? 13? Can we evaluate h prime of 10? Yes, we can. We got it. H prime of 10 equals 1/13. So the key here was using the relationship between f and g, that they were inverses twice. First, to generate an expression for h prime, right, by using the composition and differentiating both sides. And secondly, for determining that ordered pair that we could utilize to our advantage. And we did that through inspection in this case. You can see how this doesn't connect directly to a cohesive unit, and so I refer to it affectionately as a hodgepodge content objective, right? That is not an overarching theme of the entire course, right? But rather something that's part of the College Board's AB curriculum, so we needed to address it individually. Our closer is going to do a nice job of summing up this derivative inverse function. So for your closure today, I'd ask that you have a written response and be ready to share with the whole class. Don't say out loud, instead write down. If f and g are inverses, then f of g of x equals blank. So the derivative with respect to x of both sides means that blank equals blank. I love FITB closures. And lastly, thus g prime of x equals blank. Okay, go ahead and share your response with the whole class. Number 1, if f and g are inverses, then f of g of x equals, Riley E. X. X. Did you get the same thing? X? Yes? Oh yeah. Advanced algebra. So 2000 late. The derivative with respect to x of f of g of x then equals the derivative with respect to x of x. What? Means that blank equals blank. There we go. Let's differentiate. So what blank equals blank, Emily?
X G of x times G equals 1.
Awesome, thank you. Thus, G prime of x is given by Colin.
1 over f prime g of x.
If we divide over that f prime of g of x, then we've isolated g prime of x, that is the derivative of an inverse function. Way to go. Raise your hand if you have your closure entirely correct. Closure entirely correct. Huzzah! Riley, huzzah! So here we go. We've got our Unit 8 stamp check. I'm going to go ahead and outline our stamp check, and then I'll pause and upload our recording. But first, I want to make sure everybody knows where to find your stamp. So we've got Bellwork for days 1, 2, 2B, our second day of graphing with calculus that we inserted, 3, optimization, 4, optimization in FTC part 2, and 5, today's change of limits, for a total of 6 red marks. Your very first day, Form A through D, you had one of those forms for a single stamp. Our A2 behavior practice was our sketching with calculus, single-sided, 1 stamp. And then just our H of X handout that you just had an opportunity to get from last time, 1 stamp. So 3 blue activity stamps, 6 possible Bellwork red marks, for a total of 9 for your Unit 8 stamp check. In just a minute, I'm going to go ahead and give you an opportunity to count those all up and get a single total, and I'll come around and individually conference with each of you to get that total for infinite campus. And I'll put it back on the slide, but first, I'm going to want to stop the recording, and so I want everybody to take a look at our OTL number 5. Your Unit 8 concept and skill guide has a mixture of concepts, skills, and review problems. That is OTL number 5, along with correct any mistakes you made on your 97 free response that you used for Bellwork. So you want to go back and make corrections on that free response question that you used for Bellwork. Remember, your Unit 8 test is next class, so you're empowered to break up your study and review time as you see fit based on your spring break schedule. So let's make that a positive thing. You got a lot of time and decide how you want to use it. I'll go ahead and put it back on the slide so that you can find your stamps, and then I'll go ahead and stop the recording.